Okay, we've already had a lot of situations in these live lessons where we have two independent random variables, but I wanted to take a quick moment here to formalize our understanding of that concept and show you the key notation for representing independent random variables. Okay, so if we have two random variables x and y, that are independent, we can annotate that with this symbol here. And the formal definition of two random variables is that for each of the possible states of x in the set of the random variable x, as well as for all of the possible states of y in the set of all the possible states of the random variable y, the joint probability of x and y occurring, of any x outcome occurring and any y outcome occurring together, is equal to the probability that x would occur multiplied by the probability that y would occur. So this might sound complicated, but it actually isn't really. All we're saying is that for any given state of x or any given state of y, they operate completely independently. That there's no influence of, if y is in a particular state, that has some impact on the probability of x and y occurring together. So we're just saying that any changes in x are completely independent of any changes in y. They never influence the joint probability of the two things happening together. So some examples of completely independent random variables is, the probability of flipping a coin and getting heads and simultaneously drawing an ace from a deck of cards. Those are completely independent probabilities, and that one's probably really obvious. But another obvious example of completely independent random variables that we've actually talked about a number of times in these live lessons as well is the probability of throwing heads on two consecutive tosses. So if you consider each toss to be a separate random variable, x and y, there's no relationship between the two tosses. Getting heads on one of the tosses has no impact on the joint probability of getting heads or tails, given that we've had heads on one of the tosses. It's completely independent. So no matter what you did on the first toss, whether it was heads or tails, no matter what you do on the second toss, whether it's heads or tails, the joint probability is always just a multiple of the two separate probabilities of each toss. Nice, so one more topic for you from amongst all of these topics that we've been covering lately on the relationships between random variables, and that's conditional independence, which builds directly on the random variable independence that we talked about just now.